So bar OA has a counterclockwise angular velocity of 2 radians per second. Rod BC slides freely through the pivoted collar attached to OA. So this one's here. We're asked to determine the angular velocity of rod BC and the velocity of the collar relative to this one here, BC. Alright, so let's start off by labeling some stuff. So we know that the angular velocity of this one is 2 radians per second, and we're looking for the angular velocity of this one here, which I'm going to call omega BC, since it's between B and C, the endpoints. So this here is going to have to be a rotating coordinate system question, simply because we have a slider here, which means that the distance between this point and this point is not constant this time, as we've seen in other questions we've done. So for the rotating coordinate system, we need to connect it to something that it's going to rotate with. So I'm going to connect it in here to this member. So let's make this the y-axis and this the x-axis, and we're still going to have the z-axis being out of page. Alright, and that's going to mean that this was drawn in the positive direction. So let's just make a quick note. So x-y axes are attached to member BC. Okay, so that's going to mean that these axes are going to rotate with whatever angular velocity we have got on this member, which we've called omega BC. Okay, so let's start off with our equation for rotating coordinate systems, and we're going to consider what's going on between B and A. Alright, so that's the equation we need to deal with and fill in. So let's go through and find each thing individually. Alright, so starting with the velocity of point A, we know that point A is connected to point O with a rigid link that's not going to change in length. Okay, so we're going to be able to treat this like all the other questions we would have done to this point. So it's going to be equal to omega for that member, which is OA, multiplied by the radius of A relative to the fixed point. Okay, so omega OA we know is 2 radians per second, and it's anti-clockwise, so it gets a K. And we're going to need to figure out the radius of A relative to O. And this comes to be a little bit more tricky than usual because of the way we've defined our XY axis. Now the y-axis is pointed in line with this member instead of vertically upward. And I should mention you can do it with the y-axis vertically upward. You're just going to have challenges in other parts in converting your things into x and y directions. Okay, so this is the way I prefer to do it, but you can of course do it a different way. As with all dynamics problems, there's multiple ways to do everything. So if we're going to try and figure out what's going on in terms of the x and the y directions on the, this member, what we can do first up is figure out the angle that sits in here. So it's going to be 180 minus 45 minus 60, and that comes out to be a 75-degree angle that sits in here. And from that we should be able to put on, so let's just draw this member here. Okay, so this is going to be where the y-axis lies. Alright, and if I draw the x-axis on, we know it's 90 degrees to this. Okay, so this is y, and this is x. This angle in here is going to be that 75 degrees. That's going to be a right angle, since we know that our axes are 90 degrees to each other. And this is a 250 millimeter long length. So all we need to do is work out what this is in terms of our x and y axis. So this was O, this is A. We want the radius of A relative to O, so the arrow goes that way, or those two in vector form. So let's write this out. So the radius of A relative to O is going to be in this direction. It's going to be 250 sine 75. It gets an I. It's pointing in the positive x direction, so it's positive. And then this length in here is going to be 250 cos 75j. Again, it's pointing in the positive y direction, so it gets a positive in the equation. So we can simplify this down. It comes to be 483.0 j and minus 129.4 I. Alrighty, so the next one that we need to consider is the velocity of point B, and this one's pretty easy because we have B down here as a fixed point. It's not going to move, so that means the velocity of that point is equal to 0. Alright, next term. So we need to work out omega cross r. So omega this time is the angular velocity of our coordinate system. So we've attached the coordinate system to member BC, so it's going to rotate with whatever speed this one here has, which is omega BC. And r in this equation, recall that it's going to be equal to the radius of A relative to B when you've got VA on this side and VB on this side. Okay, so let's pop that in as well. So omega BC is the one we're trying to determine, and we've drawn it in the positive direction, so it's just going to get a K on the end. And we need to work out the radius of A relative to B. So let's just scroll back up. So that's this one in here, and it's along the y-axis. So maybe I'll just draw this one up here. So let's draw a triangle. We'll draw this big one that sits in here. So we know this is 75, we know this is 45, we know this is 60, and we know this one is 250 millimeters. So what we need to do is work out this distance in here, because that's basically going to be our radius that we're looking for. So this is not a right angled triangle, obviously, so that means we're going to need to use either the sine or the cos rule to determine the distance d. So the sine rule is A on sine A equals B on sine B. And I think that's the most appropriate one since we have all the angles and we also have one side. So if we use this side, it's going to be 250 on sine 60. The opposite one is equal to D, the one we're trying to find, on its opposite, so sine 45. And from this, you find out that D is equal to 204.1. Okay, so we just need to write this in terms of the radius of A relative to B. So this is point A up here, this is point B down here, so the arrow is going to go that way, and recall that the y-axis is in line with this. Okay, this is y, this is x. So that's going to mean that the radius of A relative to B is just going to be whatever D is, so 204.1, and it's in the positive y direction, so it just gets a J. Alright, so this here gives us the radius that we needed, the radius of A relative to B, which is 204.1 J. Cool. So multiplying this out into vector form, we get that. Alright, so we only have one term left that we need to deal with, which is VREL. And recall that this is the velocity measured by someone standing on the coordinate system and rotating with that coordinate system. So imagine that I'm standing here at point B. I'm going to rotate with this member here. Alright, all I'm going to see in terms of how A moves is whether it moves away or toward me. Okay, because I'm standing on this member, I'm only going to see, what happens in terms of how far away this gets from me. So because we're looking at the velocity, we're going to be looking at, so it's going to be on the y-axis, it's going to be y dot j, okay? So that's how we normally write it. If you had an x component, so it could move in the x direction as well, then of course you'd include that. But yeah, so what we're saying here is that y dot is in this direction, positive y, okay? And it's going to be moving either away or toward me. If it comes out negative, that means that it's going the other way. Alright, so now we just need to put everything back into the equation. So it's going to be this. Sorry. Okay, so we end up with that for our equation. We have two unknowns, omega BC and y dot. So it's just going to be using the I and j parts to answer the question. So for I, we end up with this. So omega is 0.634. The units are going to be radians per second, and it's come out as a positive value, which means it's going to be rotating anti-clockwise. So the other one we need is from the J's. Okay, so what this tells us is y dot, which recall was equal to v rel, is equal to 483.0. The units are going to be millimeters per second because we measured everything in millimeters, and it's come out positive, which means that the direction was correct. So up here we drew that y dot was positive going away, since this was the positive y-axis direction. So that means that this point is going to move up the bar, so it's going to be like this. So that's all there is for this question. See you next one.